So far, the goal of our presentations have been to demonstrate that energy is being created from the flow of electrons. We haven't looked into this a lot so far, but we will attempt to do this very soon. Now, before I get there, one thing that I really want to make sure everybody understands is that when we're thinking of a gradient of any kind, a difference, say in height, there is energy that is part of a gradient. So for example, think of if you go up on a hill, if you go up your bike on a hill, you will definitely feel that you need to spend more energy going up than if you need to come down, right? So if you're higher on a hill, gravity will pull you down. So the potential energy you acquire while going up the hill, you will gain in kinetic energy when you come down. In reverse, as you go up, your kinetic energy decreases. You need to spend more energy. You'll feel that in your legs. But at least when you go up there, you accumulate potential energy. Once you reach the bottom, after you coast for a while, your bike, if you're on a bike or on anything, in a car, if you don't apply any force to move forward, you will eventually stop. And the reason why you stop is that there's no more energy that is stored in your vehicle. It just stops. So what I want to show here is that whenever you have a gradient, as long as you maintain that gradient, you have energy. When this gradient stops, or if you create a situation in which you destroy the gradient, then in that case, you cannot extract energy anymore. So here's what I want to attempt to do here. So, this is an example, and this example here is a hydroelectric dam, right? So we know that energy, whenever you have a flow of rivers in a country, a province, we can construct dams. And what the dam does is that it blocks the regular flow of water. So we had a river here, and we still have the river right here. And what has been done here is that there was a structure that was constructed in order to prevent the normal flow of the river. So basically, water will flow from point A to point B, for example, right? It will flow. However, in order to flow, it will need to go through this structure here. So basically what's going to happen is that water molecules here will have to go through all of this here in order to get to the other side right here at point B. So what we do here when we want to create energy from this flow of water, we connect through the construction. We put a generator here, and what it does is that there is a turbine right here, and that turbine, every time water gets in, the turbine will turn. And as it turns, it creates power through a generator, and this will get to our houses. Now, my point here is not to explain how a powerhouse and generator and turbine works. My point here is to explain that when we look at the difference in height between this point here, so let's maintain this point here, between this height right here and the difference down to the river right here. So let's say this is a height, let's call it H. As long as we maintain this height, we will be able to have water that flows down here. If at some point the weather is so dry that the water now on that side here of the river. Let's say that the level reaches a low level here. Well, you know that water will stop flowing, right? So as long as we have this here, as long as we have water that's at least a bit higher than the level here, we know that water will flow. Why? Well, because we have a gradient, because we have a difference in height between this part here, which corresponds to the river on one side of the dam, and this point right here, which corresponds to the other side of the dam. As long as we maintain this gradient here, energy will be created. But when we have h equals 0, so which means that there's no difference in height, the energy created will be 0, because water, there's no way it's going to flow just because we need it. It needs an incentive to do this. It needs a physical reason to do this. And the reason is the creation of a gradient of some sort. Now keep that in mind, because we will apply this analogy of a gradient, and we will apply this now to the mitochondria, and we will see that the creation of energy, which of course is not electrical but it's chemical, and the creation of this energy will depend on a gradient as well. Of course, it's not a gradient in height, it's not a physical gradient, it is a chemical gradient, and you need to keep that in mind from now on. Now let's say that I have a membrane here, and let's say that we have two sides. Let's imagine that's right here, that's inside the cell, and then right here, that's outside the cell, right? So we have our phospholipids here, we have the polar heads right here, and then we have the hydrophobic tails here. So we know that the membranes are organized in this way. So we have a highly hydrophobic environment right here in the middle of this membrane, and on the outside or on the inside, we know that we have water on both sides, right? So we have water here, inside, say it's a cytoplasm, and outside is the extracellular water that is part of any organism. So we know now that we have this barrier here that prevents molecules such as ions, whether they're charged positively or negatively. These ions cannot travel through the membrane like this. They need to be transported from one side to the other one, right? So what we have here is a molecule, and let's imagine that this molecule here is a passageway through which some molecules might travel. So let's just imagine that we have a positive ion here, and that positive ion might hitch a ride through this molecule here and then be transported on the outside. So it is possible to imagine that we could open up a hole in this in this molecule here, which is a protein, and then when the hole is open, when the door is open, then it is possible to imagine and understand that some ions will be pumped, will be moving from one side to the other. Now, what I said is pumped, right? So what I mean by that is that it is possible to see that a molecule like this one would take the ion on that side here, and through some kind of a mechanism, push the ion to the other side here. Okay, so that's the part one that I want you to know for now. Now let's just imagine that we have a lot of ions on one side, a lot of positive ions. So let's say they're protons, H+, right? So we have a lot of them, but we only have a few on the outside, right? So what do we have here? Well, we have a lot of positive charges here, a lot of ions, positive ions on one side, so on the inside, and we have very few on the outside, just a few of them. Well, what do we have? What do we call this when we have more of one thing on one side than the other one? Well, yeah, of course, you guessed it. This is a gradient. Okay, this gradient here is a chemical gradient, and whenever we have a gradient, whether it's like height or chemicals or whatever, there is a potential energy that is stored in the gradient. So say that I punch a hole in this membrane here. Say that I open up a passageway in this molecule here, and I never close it. Right? So let's say that I have some kind of drug that I can apply to this cell, some kind of a molecule that opens up a passageway through this molecule here without shutting. So basically it's an open window. The window is shattered. So what's going to happen to all of these ions here? Well, you know what's going to happen to all of these ions here. They're all going to go on that side here, and then the movement of these ions is going to stop when we have the amount of positive ions on the outside will be equal to the amount of the ions on the inside. When they are equal, there will be no more passage of these ions to the membrane. Okay, so as long as we maintain a gradient, as long as we maintain this gradient here, we will have a flow of whatever is being allowed to flow. These molecules will flow, and in this case here it's ions. And I'm mentioning this here because this comes it's important to understand for then what the next step is. But just remember from this part right here is that as long as you have a gradient, and in this case it's a chemical gradient, as long as you have a gradient, you maintain a certain amount of energy, and that energy can be converted. We know that energy can be converted. So one type of energy can be converted into some other type of energy. And we will exploit that, or the cells exploits that, when it's time to create ATP. Okay, now we're going to complicate things just a little bit more because things are not always that easy, are they? So again, this is our membrane, and we have water on both sides of that membrane. We have the cytoplasm here, so of course that's inside of the cell. And then on that side here, we have, oops, okay, that's better. So right here we have the outside of our cell. Okay, so now I said I'm going to make things a little bit more complicated. Let's see what I mean by that. So let's say that I have the same ions I had before. So let's just imagine positive ions, and we know that these ions, because they are charged, there's no way they go by themselves through the membrane. They need to be transported through a molecule here. Now let's say that I have a few ions on that side, and I have way more on the outside. So it basically is a reverse situation we had before, where we had more on the inside and then they moved out on the outside. So just as an analogy, think of a balloon, for example, right? So when you have a balloon, and so that's my balloon and that's my little string, there's a lot of air, oxygen in that balloon here, right? So if I poke a hole through that balloon, we know what's going to happen. It's going to deflate and flight in all sorts of directions, right? So we know that there's energy that's stored in this balloon because there's more air on the inside than there is on the outside. Now let's say that this single ion that I have here, let's say that I open up a hole in this molecule here, and I want this single ion to go and join the others. Remember that there is more of the ions right here on the outside than there are in. So let's say that we have this molecule that opens up, and I want to transport this ion on the outside. So what's more likely to happen, do you think, spontaneously? Is it that this ion will go through this molecule here and join the others, or that these ions here are going to get this way here on the inside until we get the outside concentration of ions will be equal to the concentration on the inside. What's going to happen, right? Well, we know instinctively, and also if we compare with the analogy of the balloon earlier, we know that these ions will be more likely to fly inside the cell than this single ion to go on the outside. Basically, what's going to happen is that the ions here will go with the gradient. They will go in, and this one here won't be able to fly to the outside just by itself while there is a large concentration on the outside. It just won't happen just like that. It's not very easy for molecules or any process at all to go against a gradient. If you want to go against a gradient, you will need to spend energy just the same way if you want to go up a hill and go up a gradient in height. You will need to spend energy to get there. It is not going to be easy. The easy way is always down a gradient, is when you're high in altitude and then on your bike you come down the hill. Going up the hill is difficult. Just imagine my balloon again, right? So let's just think about that. My little balloon here, that's full. My string here. So this balloon here that's full, just imagine that I poke a hole in it. Well, how likely is it that air is going to get back in the balloon and inflate it again, right? No way. That's never going to happen. Well, when you think of a chemical gradient like this, wanting this molecule, this ion, single ion, to go against the gradient and join the other ones, it seems just as impossible as it is for the air to go back inside the balloon. So in order to do this, in order to make this possible, because cells can do that, we will need to spend a certain amount of energy doing this. So if I want this ion to join the other ones on the other side and go against the gradient, I will need for sure to spend some kind of energy right here. I will need to inject enough energy so that this ion will need to go through this energy barrier. Okay, so I need some kind of energy. Now, this is inside a cell. We're thinking of a cellular system here. I'm not talking about going up on a bike, on a hill. I'm talking about a cell, and I'm talking about the transportation of very, very small ions and molecules. And I'm talking about the passage through a membrane. So now, what kind of energy do we know can be used for such purposes? And I'm not talking about ATP here. I'm talking about something else. The goal of all of this here at the end is to create ATP. And this is what we're going to explain. Now, I'm just breaking this into smaller steps so we can see the big picture at every single part of this journey. But what kind of energy do we know the cell has that can allow processes like this to happen? Well, the kind of energy we're talking about, they're electrons. We know that electrons, once they are extracted from glucose, we know that these electrons are high energy electrons, and we will use those electrons to transport molecules from one side to the other. And if we did not have this kind of energy available, these processes would be absolutely impossible. So the next step here is to explain that. Inside cells, there's always a lot of chemical reaction happening, so biochemical reactions. And let's just use this model here where I have a molecule C that is converted into its components, so say A plus B. So because C is broken down into two subunits, we need to break a covalent bond somewhere. If we break a covalent bond somewhere, we know that electrons would be liberated. Now, when we think of electrons being liberated inside a cell, we need something to capture those electrons. So what we have in order to capture those electrons is a molecule that we call NAD+. So that molecule NAD+, as it captures the electron, will transform into NADH. We've seen that before. So let's say that this molecule here, this protein, this transporter right here, let's say that it has a little spot here where NADH can bind. Okay, so every time we have NADH, NADH now binds to this molecule here. And then when it binds to it, then a little door opens up and allows the passage of selected molecules from the inside to the outside, right? So NAD plus cannot bind here, but NAD can. And then when NADH can. And then when NADH binds here, there's a change in the structure of this protein here that allows the opening of a doorway through which molecules can flow through. Now, the change of shape of this molecule here demands some kind of energy. And that kind of energy, of course, is given by the electron that comes from this reaction here. This electron is now stored in NADH, and NADH will bind here and make sure, and provoke the change of shape. Because of this energy, it will now be possible for an ion such as this one to go against the gradient and be transported on the other side, but not without any energy. It would not be possible. So basically, this change here is provoked by the release of the electron through this that's coming from this reaction here, and this electron is stored in NADH. NADH binds, and because it binds, our molecule here is free to join the others without the others trying to get back in. Okay? So that is how the cell will use the energy from the electrons. For this next step in our presentation, we will be looking at the membrane system of mitochondria. So remember that mitochondria are small organelles that are found inside many cells, and that there are many mitochondria per cell. And mitochondria are the powerhouse of the cell. So basically, this is where the ATP is being generated. Now, what I want you to remember here is that the mitochondria, when you look at it, it's a system of membranes, right? So we have the outer membrane here, right there, as depicted here. And then we also have a folded inner membrane. So basically, the inner membrane is bigger. It has more surface than the outer membrane. So this is why it's folded like this. And the folds are called cristae. So when we look at the inside part of the mitochondria, we do have the matrix. So the matrix is also found right here in the middle of a diagram. So basically, what we have here is the outer membrane here, the outer membrane here, and this is the inner membrane of our mitochondria. Now, in between those two membranes right here, and also found right here, we have what is called, so basically what we find right here, I do have the wrong color, but just to show that in this part right here, we have the intermembrane space, okay? So that's what's happening there. So now let's just keep that in mind for a second. We have seen previously that glucose, which is a high energy molecule, can be broken down in smaller pieces, and one of those pieces is acetyl coenzyme A, remember, a 2-carbon molecule, and that this molecule can make its way inside the mitochondria, inside the matrix. Once acetyl coenzyme A has been produced, it can now enter the citric acid cycle, and through the citric acid cycle we will create a lot of NADH. Okay, so electrons will be extracted one by one and captured by NAD in order to create NADH as seen here. Now the goal is to create ATP, and what I want to show now is how this process, this biochemical process, is being exploited in order to create ATP. So I want to bring your attention to the structure of this whole thing here, found inside the inner membrane. So what we have here is a series of molecules here, proteins, right here, and those proteins can open up and close in order to allow ions to go in or out. Now remember that we have here a higher concentration of protons on the outside than we have on the inside. So that's why I have like a smaller symbol here, just to demonstrate that. So we have less protons on the inside than we have on the outside. Now what we want to here is exploit the electrons, the energy from the electrons, to pump, to create a gradient inside the mitochondria. So the gradient will be produced when we pump enough protons on the outside so that they're in a higher quantity than what we find on the inside. So how is this going to work? Well, we know that the citric acid cycle will go on, and we know that electrons will be extracted. Because electrons are being extracted, they are stored in NADH. Each of those molecules here, each of those proteins here, have the capacity to interact with NADH, and every time they do so, this little channel opens up and allows the protons to get out against the gradient. So you see, the citric acid cycle, the goal of this cycle here is to create enough NADH to trap enough electrons so that those electrons allow the transfer of energy to those proteins here in order for the protons to join a higher quantity of protons on the intermembrane space. But this goes against the gradient, and because it goes against the gradient, we need energy in order to do so. Okay? So that is one of the important pieces of this. So we see that the electrons coming from NADH are accepted by this molecule here, and then this opens up a channel that allows a proton to go from the inside to the outside into the intermembrane space right here. If the electron stays here, the channel remains open. But at some point, we don't want this, because we don't want these protons to fly back, to flow back inside, right? So we want to open up the door just long enough to allow for one proton to go through this door. So if we want to do this, then we need to remove this electron as soon as possible. So what's going to happen is that this electron is now, once it interacts with this complex here, that's called complex number 1, as you can tell here by the Roman numeral. So as soon as possible, the electron will move on to another molecule, and then to another molecule, and then again to another molecule, and again to another molecule. So you see, it jumps from one molecule to the other to another protein, and that allows the opening of a channel. It moves on to another protein, and then to this protein here that is another tunnel, creates another tunnel to allow for the passage of a proton. So you see the electron, this one electron coming from here, will be transported from here to here to here to here to here. So basically what it does is that it flows in one direction. In order to keep the electron flowing, this is why we need oxygen, because oxygen will be the last acceptor of electrons. So you see, 1 to Q is an electron acceptor, but Q is not as good as keeping the electron as 3 is. So 3 here will pull more on the electron than Q does. So therefore, there will be a tug of war. The electron will now flow to 3, and to cytochrome C as seen here, and then to complex number 4 here. And at the end, the one that pulls all the electrons towards it so that the electrons can flow through is oxygen. When oxygen reacts with the electrons, and the electrons always are transported and they interact with protons, when that happens, water will be created. So you see, this is absolutely why we need oxygen in order to keep the electrons flowing through this system. So let's just look at what we've seen so far, okay? So we've seen that we can have a membrane. I'm just going to simplify it. And then that membrane can contain proteins. So we know that already. And we know that some of those proteins can be what we called channels, right? So this is what we have here. We have a channel right here. So if we have a gradient that is being created, so say that we have a high concentration of protons on the outside, and then we have a lower concentration of protons on the inside. So this is our membrane here. We have the outside and we have the inside right here. We know that if we want to have protons going through the other side and join the higher concentration here, we know that at some point we will need a certain amount of energy in order to do this. We also know that if this happens in a mitochondria, and in this mitochondria has a certain amount of proteins and enzymes that allow the extraction of electrons from glucose and all the molecules are being degraded after that. We know that we can harvest the electrons. So what I've done before is to just show a reaction where we have a compound that creates A plus B, and then we extract an electron from there, right? So we extract an electron. So from NAD plus, we produce NADH. So if we want to go against the gradient, so join a higher concentration of protons, we will need to use the energy that is stored in the electrons that's now part of this NADH, right? Remember that the electron is right here, is being extracted from the covalent bond. So it joins with NAD and creates NADH. This NADH here will bind to this protein right here. And by doing so, transfer a certain amount of energy in order to open up a pore in which the proton will be able to move on. Because we want this door, this channel, to open and close, so that we allow only the passage in this direction but not in this direction, which would be the natural way of going, right? Because it would be not against a gradient, but it would follow the down gradient, so that would be more natural. So we need to close it all the time. In order to close it, we need to remove the electron. So the electron will now move on to another protein, to another molecule, and then so on, and so on, and so on. In order to do this, the mitochondria has a trick. And what it does is that it uses oxygen that we breathe in, and it transforms this oxygen into water. And then because we bring a lot of oxygen in our lungs and in our blood and in our cells and in the mitochondria we have, the electron keeps flowing this way. And these molecules here, these channels, keep on opening and closing all the time. So we can create a large gradient of protons from the matrix that's right here. The matrix is right here to the intermembrane space. Remember, this is the intermembrane space. So from the matrix to the intermembrane space, we create this gradient. And this gradient will now be used to create ATP. So this is where we're at right now. So our next step is to look at how ATP is being generated. If we want to understand how ATP is being generated and how the gradient is being exploited to create ATP, then we will go back to our dam analogy. Not the dam analogy, but the analogy of the dam. That's what I meant. So let's look at our dam here. So we have a construction, and that construction cuts a river in half, right? So we have on one side, we have a low level of water right here. And then on the other side, we have a high level of water. And the difference between those two levels, which we'll call H right here, determines the gradient, right? So we have a difference here. And we know that water will flow through this dam, will flow through it, and it will be attracted from this side here to this side here because of this difference in height right here, which is the gradient. So basically is the potential energy that is being stored in this difference right here. If we allow the level to be equal on both sides, right? So on this side here and on this side here, say that the level is equal and H equals 0, then in that case, the energy that is being stored also equals 0. Okay. So now let's look at the cell. So let's keep this on the left of the panel here. And now we will look at the cell. We know that if we look at the membrane, we have our membrane here. And then we have on that side here, we have a gradient that's being generated. So we have a certain amount of protons on one side, and we have a lower amount of protons on the other side. So right, look at this here, water level, compare this to the water level right here. So this is, of course, this is higher than this one here, which is lower. Now, we now have a gradient, and that gradient is a chemical gradient, right? this here was water gradient, a physical gradient. So now we have a chemical gradient that is stored in this difference in concentration. Well, this is going to be exploited by a very important molecule that kind of looks like this. So here, this is the intermembrane space, remember that. And this here, this is called a matrix, right? So it's the inside of the mitochondria. All of this happens in the mitochondria, just in case you forgot. So what we have here is a molecule that we call ATP synthase. So the ATP synthase has a capacity to take ADP to transform it into ATP. And it does so by reacting with a phosphate. So it brings ATP and ADP and phosphate together in order to create this molecule here, which is a very, very important one. Well, the ATP synthase will be able to do this reaction, which of course is a highly non-probable reaction. It's totally not spontaneous because ATP is very unstable. It's way more unstable than ADP is. So ADP prefers to stay this way than ATP. Remember that there are negative charges on ADP and negative charges on the phosphate. So if we want to bring two negative charges together, we'll need to spend some energy somewhere, right? It's always the same thing. How do we spend this energy? Well, remember that water here flows from the highest point to the lowest point, right? So it follows the gradient. It follows the gradient from the high part of the gradient to the low part of the gradient. And this way, we can generate electricity. Now, if we come back to our mitochondria example here, we have a higher concentration of protons on that side here, on the intermembrane space, and a lower one right here. If I open up a little small passage in our ATP synthase here, what's going to happen? Well, those protons will, for sure, be attracted to the inside of the matrix. They'll do so spontaneously. And what's going to happen here is that because they do so spontaneously and they follow the gradient, they use this potential energy stored in chemical energy. They will use this in order to transfer the energy to this ATP synthase here, which is going to create ATP. Okay? So ADP and phosphate will be linked together by the fact that this ATP synthase can now capture the energy of this proton gradient, and the protons come in from the outside, they fly into the matrix, they travel into the matrix, and by doing so, transfer their energy to this reaction here, which now makes this possible.